Hi there. My name is Ian Sharp. Today I will be talking to you about the biophysical properties of tropical dry forests, especially in the Americas, as this is the location of my current research and is the topic that a lot of our research in Tropi-Dry looks at, is specifically in the Americas. So, first is the outline of what I will be talking about today. So, our first subject will be setting up what are tropical dry forests, what makes them unique, and then trying to understand how forest succession works. This is especially important for tropical dry forests, seeing as a lot of their historical range that they used to occupy has been cut down. So, a lot of the old growth primary forests that originally existed when the Europeans came over um, is gone. So, a lot of the forests that we study nowadays is called secondary growth forest, or a forest that is starting to recolonize that historical range that used to exist. So it's really quintessential to be able to understand what forest succession is and what are the mechanisms that drive forest succession as well. Then we will go into the second topic, which are indicators of tropical dry forest health. A lot of these are more modern remote sensing types of uh, techniques trying to identify vegetation health. These are very good to use because we can use satellites in order to get these vegetation products like the normalized difference vegetation index or the fraction of photosynthetically available radiation, which then allows us to be able to monitor vegetation health on a global scale. So a lot of these are more modern methods. Then we will talk about the applications of these vegetation indices, and then I will have my concluding remarks. So here on this map, the these orange bands you can see around the world are representative of tropical semi-arid forests or tropical dry forests. And as you can see, they do extend to a large degree around Africa between the Tropic of Cancer and the Tropic of Capricorn. And essentially, if a region isn't occupied by a tropical rainforest, it's typically occupied by some type of tropical dry forest, especially in the lowlands of countries and and on the plains. Sometimes we'll see that tropical dry forests uh, start to emerge from savannas that used to exist, and or from pasture lands, ranch lands, etc., etc. In the Americas specifically, we can see that they occupy a lot of the Pacific region of Central America here, and they used to extend down even further along the Pacific coast here, right down to the tip here of Peru. And we can see that even in around surrounding the Amazon, we have a lot of this tropical dry forest that still exists. So, what makes tropical dry forests unique is that they go through a dry season for 3 to 6 months every year. So, at this point, the leaves from lots of the species in the tropical dry forest start to drop, and you actually have just kind of like what you have in North America in the winter when all the leaves drop. It's the exact same phenomenon, but because it's a dry season, it's driven by precipitation, so that for 3 to 6 months, there's just a real lack of precipitation. In the other 6 to 9 months, uh, with the wet season, they exhibit a precipitation range between 700 to 2,000 millimeters per year. And in the wet season, temperatures usually become lower, which gives us this annual average temperature of 25.5 degrees Celsius. The tropical dry forests do occupy about 51% of the total tropical regions worldwide. As you can see, even here in India, Southeast Asia, Northern Australia, they occupy quite a lot of land compared to the tropical humid forests or tropical rainforests. And they actually occupy 42% of the total vegetation, tropical vegetation worldwide. So they're a pretty large ecosystem, and despite this fact, they are a severely understudied tropical ecosystem because, as we can see here in this current extent of tropical dry forest range in Latin America, a lot of that tropical dry forest has disappeared. This started to happen in uh, the 1700s when farmers started to cut down tropical dry forests because the land that tropical dry forests usually uh, thrive on is actually really good farmland as well, or pasture land for ranching or other types of pastoral activities. As we can, as I was saying though, we can see that tropical dry forests are starting to come back. A lot of them, but we will discuss this in a bit. So, what makes this tropical dry forest unique, especially in the Americas? Well, it's that a lot of the tropical dry forest that we see now is not primary forest, which is the original forest that has not been cleared or deforested. About maybe 1 or 2% of the total extent of tropical dry forests is primary forest. And so a lot of what we see for tropical dry forest now is a secondary forest, which is forest that has grown back after a deforestation process and is in the process of reforestation or recolonization of its historical extent. So this is what makes tropical dry forests unique, and that they have a high biodiversity and a high rate of endemism as well for their species that do exist, because a lot of these species are drought tolerant species, especially the vegetation, where they have very unique life history traits that have allowed them to cope with the extended drought periods every year. And because of this, there's a high rate of endemism that is comparable to tropical rainforests. But because these forests you might are not as sexy, you could say they don't get the advertisement that the tropical rainforests do, or even the research that tropical rainforests do. So this is what makes this area of study really interesting. Now we're on to forest succession. So forest succession is essentially how does the forest come back into an area that it used to exist. So if we start here on the right side with our pasture land, this is what it used to look like when it was being ranched, typically. And we'll call this ground zero, or in this slide, probably stage 3. We still have the grasses and the perennials, but we don't really have, except for these nuclear trees that you can see here, we don't really have too much other types of vegetation there. After pasture land has been abandoned, typically in the 5 to 10 years that follows, we start to see trees coming back. So we start to see this stage 4 or even early stage 5 type process that is just small, fast growing vegetation that, yeah, their traits are typically that they grow very quickly, they can occupy space very fast, and so that's how they outcompete other types of vegetation or other species, is just by their high growth rate, high reproductive rate, uh, and low competition or capabilities competition against the later stage forests. So after about 5 to 10 years, when their tree height typically reaches around 10 meters max, they start to transition into these intermediate forests. So the intermediate forests, they're starting to have a more mature canopy. You'll actually start to see lianas or vines start growing on these trees, uh, competing for resources, especially in the dry season when lianas are the most competitive against their trees that they exist on. And you start to see some more undergrowth of the forest, a little bit more developed undergrowth of the forest, and trees start to get taller as well, usually around 15, maybe 20 meters in height. And this usually lasts up until it can last up until 20 to 30 years. It really depends on the density of lianas that exist within the specific community, because lianas, seeing as they're so highly competitive with the trees that they grow on, they are actually capable of arresting the development of forest succession from anything past an intermediate stage. And they do this by uh, being able to create these mats in the forest canopy. So they would create mats like up here, and these mats actually will create such uh, high amounts of shade that the later stage vegetation that would start growing in the understory during the intermediate succession stage cannot actually develop because they don't have the resources like sunlight available to them to be able to do so. And in particular, lianas, they thrive so well in tropical dry forests because during the dry season, they have a really deep root system that is capable of acquiring water from the water table that these trees can't access. So that's why they're capable of being able to thrive during the dry season. And this is typically when lianas can start to take over and infest a community or an ecosystem. So if there is no liana arresting of the arresting development of the forest succession, then we would go into the late stage. There you can see here that the late stage, there's lots of tall trees, mature canopy. This is when you start to get like the more three-dimensional structure of the forest, where you have the canopy and the understory as two very distinct layers, and even micro ecosystems where species thrive in one or the other but can't occupy both niches. So this is how forest succession typically works. Um, Usually, a forest succession can be reset if it experiences a disturbance like fire, which is a very predominant disturbance force in tropical dry forests. If humans come along and clear the forest again, even flooding events can occur, arresting forest succession or even reversing it. But dependent on the disturbance regime, so the amount of times that a forest gets disturbed or the frequency that a forest gets disturbed, can really determine how fast a forest will mature and how fast it will transition between each of these successional stages. So here in the early stage, we have forest with patchy open canopy. You see a lot of these succulents occupy this type of forest um, because they can access sunlight so easily. As you can see, these trees don't have a whole lot of leaves on them. There's not really much arresting the development of the undergrowth here. But you can also see that the vegetation is fairly small. This would be about like a 8-meter tree maybe. So yeah, these are usually pretty young forests. Yeah. So the intermediate stage, you can start to see here that you're getting more developed canopies. A lot more leaf cover and shading is occurring in the understory. And you can even see in this picture here that you start to get these thick vines starting to crawl up the trees. And you can see that if the infestation of lianas was great enough, that you could really start to arrest the development of any of the understory vegetation, which is when this is usually the stage that the late stage species would start to colonize the land. And if they can't get any resources in the understory here because of the liana infestation, then you'll get arrestment at this stage. And so quite a few secondary forests can actually get arrested at this stage, specifically because the lianas, with the changing climate, can deal with droughts even better than the hosts that they live upon. And so there's a theory running right now that we will actually start to see a lot more intermediate stage forests as climate change progresses, because the severity of droughts might get worse. And so lianas will have an even better competitive edge over their host species. And then we have these beautiful late stage forests, which not a lot of them exist right now in the Americas. Those that do exist are typically found in national parks nowadays. There's very few outside of national parks or private reserves that are still in existence. But these forests are typically 50 years or older in age. Um, they have two distinct layers: the canopy and the understory, which is occupied by shade tolerant understory plants. And this is usually when we see higher amounts of biodiversity is in the late stage, although depending on the disturbance regime, sometimes the intermediate stage can actually occupy just as much biodiversity or even greater biodiversity than the late stage. But yeah. So, what are the determinants of forest succession? Well, uh, there's some main drivers here, and we'll start with pollination and seed dispersal. So there's two different types of pollinating and seed dispersion. One is where you depend upon invertebrates, like this fly here, or vertebrates, like these monkeys, to pollinate your flowers for you and go from flower to flower, pollinating them, and even taking the fruits from trees, eating the fruits, and then dispersing the seeds in their fecal matter or in their fur. Sometimes there's species of plants that have burrs, like spiky seeds, that'll just get caught in the fur of an animal and be transported that way. But so there's specific species that have specific strategies adapted to this, and you can really see in the forest succession what type of um, seed dispersion would be predominant because of the types of species that exist in that ecosystem. The other type of seed dispersal or pollination type is wind pollination and seed dispersal, which is probably the older um, life history trait in plants, especially when they first colonized land. This was how it was predominantly done before vertebrates were very populous in these ecosystems. So, but like I said, other um, species have developed or kept these older life history traits, and you can tell when a forest is uh, under reforestation what type of uh, species are nearby, because you have to be within relative close proximity to where the forest is going to start to reforest in order to be able to uh, occupy these spaces. Another determinant of succession that I touched upon already is liana infestation. With high infestation can result in successional arrest, stopping species at the intermediate stage or stopping forests at the intermediate stage. Topography can have a big impact because depending on where you are topographically, it determines how much runoff you might receive from rainstorms, how much erosion is occurring at that particular spot, what type of soils are being deposited into the basins that the forests might occupy. So some forests, some tropical dry forests might have the ability or the resources of 5 to 10 meters soil depth with high nutrients because it's at the bottom of a hill. Yet the trees that occupy the very top of that hill have very shallow soil depth because it keeps on getting washed away and eroded away and deposited into the bottom of the basin next to it. So this can really affect how fast forests grow, uh, how big trees can develop, or even how far a forest succession might be able to go. If you have very shallow soil that is low in nutrients, you will not be able to develop a forest very quickly, and it might even be arrested at the early successional stage or something like this because um, just because of the soil type. And then, like I had previously discussed, the proximity of the forests to open land or colonizable land. So if you're deep in the middle of the forest, you're a lot less likely to be able to get your seeds to the colonizable land than if you are on the edge of the forest. And so, really, the edge effects of the forest really determine the speed and the progression of reforestation in lands that are colonizable surrounding the forest. So, next, we'll start talking about how we actually measure forest health. And we'll start with talking about the phenological cycles. So, the phenological cycle is the yearly cycle of vegetation growth, essentially. Um, this, depending on your definition, can mean when leaves start to bud, or when leaves are in full growth, like they've fully unfurled and they are photosynthesizing. It can be when flowers start to bloom, or when fruits start to develop. But for our sake, we will define it as first leaf bud, and we usually measure the phenological cycle using some other technique. For this example, we will be using a FAPAR, so the fraction of photosynthetically available radiation to measure phenological growth. So there's 4 phases of the phenological cycle. There's green up, maturity, brown down, and dormancy. So the first stage, green up, usually occupies this band right here that we can see. It's when the forest starts to go from this brown no leaf stage. You can start to see leaves are starting to develop now. The rainy season has started. Usually, what triggers green up is soil moisture content. So once soil moisture starts to get up towards like 15-20% soil moisture content, then the trees know that the wet season is about to start. So then they start growing their leaves again. So this can last usually between 9 to 15 days. So it's a really quick transition from this dormant state to the maturity stage. So this is when a forest is in full maturity. It is photosynthesizing at its maximum. As we can see here, it's plateaued pretty much. and it's when seeds and fruits start to get developed, because now the species and the vegetation have the energy resources to invest in their reproductive cycle. So now they start to develop the flowers, and then they start to develop the fruits after the flowers have been pollinated, etc., etc. So this can last for the majority of the wet season, typically like 2 to 5 months, somewhere around there. And then once the wet season has ended and soil moisture content starts to go back down, the leaves start to shed their leaves. So this is when the leaves go through senescence, is what it's also called. And this is a little harder to track using remote sensing techniques, because the pigments that are in the decaying leaves still can retain photosynthetic radiation. So usually when you're monitoring this remotely, it can be a little bit delayed, or it's a little hard to tell when senescence has actually started to occur, unless you have some sort of physical evidence here of when you can actually start to see the leaves browning. This plant in the foreground is a very good example of such. And these plants in the background are a great example, actually, of why it can sometimes be hard to detect when brown down or senescence is occurring, because they can stay around on the trees for a long time and continue to absorb radiation despite not actually photosynthesizing. And then we have our dormancy stage. This is during peak dry season. Can last anywhere from 3 to 6 months. This is, I believe, in Santa Rosa National Park. And so there it lasts from 3 to 4 months typically, from end of November, beginning of December until about April, late April, beginning of May. So why is it important to even analyze the phenological cycle of vegetation? Well, from the example that I've given you right here, you can actually see that with the phenological cycle, we can start to monitor between years. So this is 2013 in Santa Rosa National Park in Costa Rica. And we start and we see that this was a fairly good growing season. There wasn't really much deviation. It seems to be fairly healthy vegetation throughout the entire maturity portion of it. And then we have this short dry season. And then here we can see that green up occurred and maturity occurred, but that for some reason there was a drop off in the FAPAR, or in the vegetation health. So this allows us to start to investigate specific time periods within a forest's history, just try and understand what exactly just drove that little divot right there in the cycle. Was it a drought, like a drought in the middle of the season? Is this becoming more prominent? Like as we can see here, the exact same thing occurred where we had green up, a little peak of maturity, and then it seemed to decrease again. And that happened in 2 successive years as opposed to this year. So which one allows us to ask questions such as which one is the anomalous year? Is it normal for us to see this brief peak, then down, then a peak again? Or is it more normal to see a very healthy, mature forest that stays green for the entirety of the wet season? So it allows us to start investigating such problems as that. And it even allows us to monitor things like growing season length. Like the 2013-14 growing season length was 267 days long. We can see when it starts, when it ends. And as you can see with 2014-2015, despite having this little divot, it actually had a longer growing season overall. So it's things like that that we can start to investigate and we can start to wonder. And that's why um, tracking the phenological cycle of forests is particularly important, especially in the cases of climate change. It allows us to help predict how are our forests going to react to the changing climate. So we'll start going on to some more remote sensing techniques as to how we track forest health. So one such technique is called the leaf area index. And what it essentially is doing is it's trying to determine the amount of leaf cover in a certain section. So it's measured in meters squared per meter squared. So that's leaf area in meters squared within a meter squared plot, like this. So how much of this vegetation occupies this meter squared plot? So there's a couple techniques that we use. One is the hemispherical camera, where we take a fisheye lens and we take a photo of the canopy above, and then we can run different types of software to actually analyze what are the gaps, where are the gaps, and then how much of this sky region is being occupied by leaves. And this is rather important in the larger scale because if you can measure the leaf area index, you can measure which regions of the world seem to be the most productive, which seem to exhibit the largest leaf area indexes. And it's really a key link to being able to help determine what the interactions between the biosphere and the atmosphere are. For example, with the Amazon rainforest here, we can see, we all know that it is a big sequester of carbon in the atmosphere, but knowing the leaf area index of this region can really help constrain our models, um, being able to give us a more realistic view of how much carbon the rainforest is sequestering, or even how much carbon the rainforest might be releasing if it's in a stressful state or situation. And so it's typically used to help constrain CO2 models. Um, that's the main use of LAI right now. And it also helps describe forest canopy structure. Like you can help determine what type of forest succession that you're looking at by the leaf area index, because obviously an early forest stage will have a smaller leaf area index number than a later stage. And so it can also be used to help track reforestation that is occurring in a region. So from this, we can also get our gap fraction analysis. So this is a hemispherical photo that was taken in Santa Rosa National Park in an intermediate stage forest. And then we ran it through a piece of software called HemiView, which essentially blacks out all the vegetation and then leaves the sky regions white. And using this type of gap fraction analysis, we can start to understand how much light is penetrating to the understory. So, how do these understory plants actually adapt um, or live with this severe depletion of radiation that keeps on getting absorbed in the upper canopy, and how does it react? So it's utilized for understanding understory light utilization, like sunspots. How does understory vegetation use sunspots to its advantage? How important are sunspots to understory vegetation growth? It also helps us understand forest structure, like such as what stage are you looking at in forest succession, and then understanding plant behavior, such as how do vines growing up trees, the trunks of trees, uh, unfurl their leaves or orient their leaves even to the sun in order to maximize the amount of radiation or sunlight that is getting through the canopy. And it's also used to help constrain leaf area index as well. So it's a proxy that kind of works together with leaf area index to help constrain it, and this further helps the CO2 models that rely on LAI. Then we go on to the normalized difference vegetation index. So this is the oldest vegetation index that's been used. It was on some of the first satellites that NASA put into space to monitor the world. They decided that they would create this normalized difference vegetation index to see if they could actually monitor forest health or not. And it turns out that they could. So, how it works is that it uses the near infrared radiation, or NIR. It subtracts the amount of visible light that is seen, and then divides that by the total amount of near infrared radiation and visible light radiation that there is. And it turns out that when vegetation is green, it reflects near infrared radiation quite a lot, whilst it's absorbing the visible light radiation a lot. So if you take the ratio between the two, this is what gives you your NDVI. So it's useful, like in this example here on the right, you can see that this green tree would have an NDVI of 0.72, whilst this browning tree that's in senescence would have an NDVI of 0.14. And NDVI is constrained to this 0 to 1 scale, typically. And it's important because, as we can see here with the remote sensing aspect of it, this is an NDVI index for 2 different years, and one is a drought year on the right here, whilst one is a normal year. And you can see just how much the drought is affecting this region by California. So it's really helpful as even a drought index. It helps monitor forest reforestation or degradation. And the long-term studies that we can get from these satellite images can actually help us understand how vegetation is responding to climatic change or intraseasonal events, such as forest fires, periodic droughts, or hurricanes even. So it's a really useful tool in order to be able to monitor the long-term health. And seeing as NDVI has been around for so long, we have an extensive history of NDVI from around the world. So this is really useful to help us understand how has the world even changed in the last 30, 40 years. So it's a very useful tool. Now, we will talk about the fraction of photosynthetically available radiation, or FAPAR. So FAPAR utilizes the fact that photosynthesis primarily occurs in the presence of radiation between that is a wavelength of 400 to 700 nanometers. And that it also utilizes the near infrared reflection that vegetation gives. So essentially, it's kind of like NDVI in that it compares the relationship between visible light and near infrared radiation The advantage of FPAR is that it isn't so subjective to the background reflectance. So let's say that you're looking at a forest from above. You're going to be looking at the top of the forest, but then with all those gaps, you're also going to be looking at the bottom of the forest or the soil or whatever is underneath the forest. And so NDVI has is more sensitive to the type of background that you're looking at, whilst FAPAR isn't as sensitive. It won't change as much per se between dark, loamy soil compared to sand. So that's why it's a really good indicator. And it's also been declared an essential global climate change indicator because it's so robust. And we have this product on a global scale, just like we do at NDVI. So there's two methods in which you can um, actually measure FAPAR. This is an example from our research site in Santa Rosa National Park. So you can have a bunch of wireless sensor nodes that have these PAR or photosynthetically available radiation sensors mounted to them. And if you have a PAR sensor on the top of a tower like this, it's going to be able to measure the total amount of incoming photosynthetically available radiation. And then if you have sensors in multiple locations around the tower or within the footprint of the tower with these PAR sensors, you can get the transmitted PAR, or the amount of radiation that has penetrated the canopy and actually made it to the understory. Now, PAR, like I was mentioning before, can be reflected by soil, by the vegetation itself, or by water and other factors. So we also measure the amount of reflected PAR that comes back through the canopy back into the atmosphere. So if you take the total incoming PAR minus the transmitted PAR minus the reflected PAR and divided by the total amount of radiation, this is what gives you your FAPAR. And this is really useful because if you have the ground measurements, they're kind of like a ground truthing site for the satellite images. Because the difference between that and the satellite is the satellite measures the amount of visible light that came back to it and the amount of near infrared radiation that came back to the sensor after it's being shot at the vegetation, and then determines what FAPAR is through a formula or through an algorithm. And so it's really a lot more theoretical using the satellite's FAPAR than if you use these ground truth sites' FAPAR, because you know that this is exactly what you're getting when at this period of time. So satellite-based FAPAR, like I just said, is taking the ratio between visible light and near-infrared radiation and then gives you a product. And so as we can see here, this is giving you a vegetation FAPAR index throughout Central America, Nicaragua, Honduras, Costa Rica. Yeah. So the applications of FAPAR are that it can be used to characterize phenology, like I showed you in that previous phenological example. It can be used to determine forest health, like NDVI, but in a slightly more robust way. It investigates the responses of vegetation to climate change. It also investigates the plant's utility of light, because not all plants utilize light in the same way. For example, with the lianas actually have thinner leaves so that during the dry season, when the radiation is more intense, the heat is more intense, it's capable of actually kind of acting like a fridge in that it allows a lot of the heat to escape the leaf because of how thin it is, as opposed to other trees that during the wet season develop these really thick leaves that are more stacked um, and can absorb a lot more radiation. So, not all plants utilize light the same way. And it also allows us to investigate the abiotic and biotic environmental effects on vegetation, such as how you could probably monitor how pine beetle, let's say in North America, is affecting forests. You would be able to see that in an unhealthy, infested forest, that your FAPAR is generally going to be lower than in a totally healthy forest. And so it allows us to monitor and understand how the ecosystems are actually responding to these different factors that are affecting. So, what is the big picture? Why is it even important to do any of this, to monitor these biophysical aspects of tropical dry forests or any type of vegetation, in fact? And it really comes down to this. It helps us understand how land was being used in the past, so the historical land use of land. So, for example, in Costa Rica, a lot of the tropical dry forest is secondary and is starting to come back in what was once pasture land or even farmland for such products as rice, sugarcane. And so, actually being able to understand what species exist within a plot can help us understand how that land was used before and how that historical land use might be impacting the land or the surrounding land today. Um, Forest succession can give us an idea of just how old uh, a forest is, how what type of ecosystem services that it is capable of giving us, and just how quickly a forest might come back in a region. And even if, let's say, we have a high rate of liana infestation, we're getting a high rate of uh, successional arrestment from these lianas, we can understand, well, maybe it's because our climate is changing that this is occurring a lot, and therefore these forests in the future are not going to be able to sequester as much carbon as we previously thought that they were going to. The vegetation indices help us measure forest health, like I've said many times now, and just how robust these forests are going to be in the future. And then phenology helps us understand exactly how are the forests going to respond in the future, how are they responding to events that are occurring currently or that have occurred in the past, and can we use that information to learn how the forests or other types of vegetation, such as croplands, are going to respond to climatic or weather events in the future. So all of these really get used and put into the forest and ecosystem functionality bin, and they're just all descriptors really of what do we know about the forest, what do we know about the ecosystem, how is it doing, is it healthy, is it not healthy, and then when we combine that with the human factors, what are humans doing to forests? How are forests going to impact humans in the future? Are they going to be able to stabilize regions, like being able to become water aquifers or be able to become resources of another kind? And when we start to combine the human factors with our understanding of how the forest and the ecosystem is functioning together, we start to understand how the ecosystem is going to respond to future environmental change and what that's going to mean for humanity. And that's a really big question, and it's a really important question to understand because these forests have been around for a lot longer than humans have. And now that they've been cut down and put into these pockets, we we're going to rely on what exists now a lot heavier than we would have in the past. So understanding how to preserve and how to benefit from these forests and these ecosystems is going to be really important in the future, and that's exactly why we need to keep on monitoring these tropical dry forests, specifically in the tropics, because this is going to be the region where it impacts people the most, is in these tropical regions with people that rely on these forests and ecosystems. Anyways, I would like to thank you for watching my presentation, and I would like to thank Tropi-Dry for hosting this webinar series so that we can be able to communicate our science to the public in general. And are there any questions?